Okay, so hi everyone. I'm Robert Kaufgamer. Welcome to the afternoon session. It's going to be like a terrific session. Let me use like a current jargon, the likes of which has not been seen before. And the first speaker is Jason Lee, who will tell us about deterministic paradigm conditions and negative wave short term.
Thanks, Robbie, for the introduction. Okay, so in this talk, we'll look at a single source shortest path problem. So given a source vertex, find the S to V shortest path to all other vertices V. And in the case of non-negative weights, of course, Dijkstra's algorithm accomplishes this problem in near linear time. Of course, still in the Dijkstra setting, there has been some recent breakthroughs that kind of solves from faster than sorting, but we will be talking about a different setting which allows for negative weights. Okay, so it's not hard to see that for negative weights, a greedy algorithm like Dijkstra fails to find the shortest paths. And in this regime, until 2022, until like a decade ago, the best algorithm for this problem was around m root n time. And this was improved to near linear time, at least for integer weights weighted graphs, by this breakthrough of Bernstein, Nanoch, and Wolff-Nelson. Right, so at a high level, what the BNW algorithm does, and what also some subsequent work does, is the computed potential function, which we'll see later in this talk. They apply, at a high level, they apply some kind of divide and conquer strategy, which we will also see. And one of the key innovations is they use a sort of graph decomposition that makes everything work. And this talk will see a similar graph decomposition that's arguably simpler and also deterministic. Okay, so let's begin with potential functions. So a potential function is a function on the vertices. So every vertex gets a real weight, gets a real value that reweights the edges so that every edge gets a new weight equal to the old weight plus the weight at the tail minus the weight at the head, or the values at the tail and head. Okay. So why is this useful? So consider a path from S to T. So consider two vertices ST, consider a path from S to T. Let's look at the new weights on the edges, and let's sum the weights. Notice that the sum of the weights telescope, in the sense that like this minus phi u here cancels with the plus phi u from the next edge. And what we get is that the total weight is just the old weight plus phi s minus phi t. So in particular, sorry, give me a second. So in particular, the shortest path is still shortest after reweighting because every path gets offset by the same additive plus phi s minus phi t once you fix s and t. Okay. So here's like a small exercise on why potential functions are useful. So here's one candidate potential function we can try, which is just for any vertex v, just let phi of v be the shortest path to v. Let's say starting anywhere. The starting anywhere is not too important. You can think of it starting from S or starting from anywhere. But the claim is that if you reweight under this potential, then all edges automatically become non-negative. Okay. Why is that good? That's good because then we just run Dijkstra on the new weighted negative non-negative graph, and then recover the weights by using this this offset guarantee. And why is this true? Why are the new edges non-negative? It's just because if you use a definition and then use the fact that these are distances, actual distances in the graph, then the triangle inequality essentially gives you that this is non-negative. Any questions so far? Okay, and here's like if you're not familiar with triangle inequalities for distances, just think of it as what is one valid way to end at v? Is to start at u, is to first end at u and then take the edge uv. Okay. But of course, so the benefit is like suppose we can find this potential function, then we just run Dijkstra because the new weights are reweighted to be non-negative. But the issue, of course, is that this potential function is defined using shortest path, so computing already requires negative shortest paths. But nevertheless, let's see one potential way we can use it. And this is by divide and conquer. So far, everything has been, this is still in the Bernstein, Nanonkai, Wolff-Nielsen's framework. The new techniques we'll introduce are later on in this talk. So here's a high-level idea. So suppose we can divide the graph into two balanced parts. And balance will be important to make the recursion small. Let's recursively solve the shortest path problem on each of the induced subgraphs. Okay. Using the distance that we compute, we can get these potential functions, and then just merge the two into a single potential function for the initial graph. Okay. So what does this accomplish? This means that the edges in both parts are non-negative. But on the other hand, the edges between parts can be negative because there's no guarantee between parts what happens. So that's pretty good at saying that at least a good fraction of graph is non-negative. And this recursion is good because the graphs, the pieces are balanced, so the recursion depth is small. And in fact, here's an ideal case where you can indeed finish and solve the problem. Suppose that every shortest path in the original graph crosses between the two parts a small number of times, let's say h times. Then it turns out there's an algorithm to solve this problem in m times h time. So I will ignore the details, but this is some kind of hybrid between Bellman-Ford and Dijkstra, which can solve the problem when every single shortest path has at most h negative edges, which will be the case here, because the only edges that are negative are between the two parts. So the task boils down to finding a good partition for which shortest paths go between the two parts a small number of times. Okay, it turns out we cannot quite accomplish this in one go. So what the BNW framework does is it actually computes an iteratively computes a set of potential functions. So let's see how this works. So let's actually define a graph G prime to be the initial graph, but all negative weights are halved. So every negative weight becomes half of this original negative weight. And the key idea is somehow, let's try to compute the shortest paths in this newly weighted graph. Either do this or find a negative weight cycle in the initial graph. So I want to kind of emphasize this is a strictly easier problem than the initial problem. Because, of course, a negative weight cycle, if the initial graph contains a negative weight cycle, you have to output it because that implies there are no shortest paths. Because shortest paths are negative infinity in that case because you can just go through the cycle arbitrary number of times. So negative cycles are important, but in this case, these are on two different graphs. And the fact that the initial graph is more negative means that this is a strictly easier problem. Are there any questions about this? Okay. But nevertheless, even though it's strictly easier, it's still sufficient to solve this problem because you can just iterate this log n times. Let's see why. So suppose of course, if you find a negative cycle, you're just done, so you can just terminate. Otherwise, you find the shortest path in this newly weighted graph. Now, what happens if you reweight under this potential? Consider an edge. In the newly weighted graph, it was non-negative because we solved shortest paths. In the initial graph, the point is that it halves in weight. Okay. Okay, so in other words, it's half as negative by these inequalities. So what does that mean? That means that you can just iterate this process some log n times, get all the weights to maybe minus 1 over poly n, after which you can just kind of round and pretend they were 0. Okay, so given this setting where we have this graph G prime, let's now prove a combinatorial property of this graph G prime as follows. So suppose we have, let's first define the graph G prime with this at least 0 to be the graph G prime with all negative weights edges replaced by 0. So replace every single negative edge by 0. And here's a combinatorial property that we want to show. suppose that this new graph has low diameter. So in other words, the distance between all pairs of vertices is small. Then if a negative weight path has large weight in this new graph, a negative weight edge in G prime. So a path with negative weight in the graph G prime, but has very large weight in this G at least 0 graph, then there must be a negative weight cycle. So in other words, we're preventing this structure from happening. Okay, so let's see why that's the case. So what does this mean? This means that the total weight of positive edges exceeds delta. This means that the total positive plus total negative in G prime is less than 0. And now we use the fact that the total positive was more than 0. Total negative was less than, let's say, minus delta. Then because the graph in G, it was doubled. It was halved going from G to G prime. In G, the weight was like less than 2 delta. So it's like doubly negative in the original graph. What does that mean? That means that like in total in G prime, it was like delta minus 2 delta, so minus delta in G. In G, sorry. And then you can close this path into a cycle with weight at most delta because this graph has low diameter. So that's roughly the proof, and this shows that low diameter structures are useful when considering shortest paths. So any questions so far? This kind of like, so far everything has been in the B&W framework, and this is where we introduce a new technique. So our new technique is called padding decompositions. So here's a high-level idea. It's going to be very similar to the idea of finding a balanced partition of the graph. In this case, let's suppose we can find half the graph such that, let's say U is like the left half of the graph. And now the set of all vertices of distance like about delta over log squared n is small. So we have a set U for which the set of vertices that you can reach with distance at most this is like a small fraction of the graph. Okay. And we call this like the padding. This is like you can pad U by this small padding. And here's like a simple but key observation, which is that any path of weight at most delta, which is guaranteed by this previous structural claim here, any path of weight at most delta in this positive graph must go between the left and the right part at most log squared n times. And that's just because every time it goes from left to right, it must go through this padding. It must eat up at least delta over log squared distance. So this is kind of one way to force the fact that any shortest path cannot go through both sides, go across both sides arbitrary number of times. Okay. And we'll do something very similar. We'll just like split the graph up and recursively compute. But here the padding needs to be duplicated. So that's important. And that's also why we need padding to be small, like 1 over log n fraction. Okay. So at a very high level, the total size grows by 1 over log n fraction. Over log n the recursive calls, the total growth is still small. And in this new graph, a path like this can only cross so many times, and therefore the entire structure works. Okay. So I'll finish by like just briefly discussing how to compute this padding decomposition. So at a high level, it's using some kind of sparse cut argument. So start from any vertex, and the goal is to find like what I call a sparse ring of distance at most dis. So how it works is like you start from a vertex, and you can imagine like carving out rings of like with delta over log squared. And we find the first layer whose like size is less than 1 over log n times the previous size. 1 over log n times everything before it. This was what's called like a sparse cut type argument. Okay. And we'll add the blue part to U. We'll call the green part a padding. and we'll just repeat this. And the point is, like, we should be able to find a sparse ring eventually, because if the next ring is not sparse, then the total size must grow by 1 over log n fraction. And this only happened like log squared n times before you reach everything. So you'll find a sparse ring eventually. Anyway, this is not quite true. Like there's a failure case, which is that the ball just grows too fast. Like for example, it could be the case that even the first level you just get everything. But luckily in that case, and here at the very high level, it's somewhat good because that means that a source can just immediately reach everything. Suppose we just repeat the process but in reverse. So suppose that we just do the same process, but like imagine all edges are backwards. And once again, suppose S can just reach everything. Then immediately you already got a small diameter graph because S can reach everything in a small number of steps. Can also reach from everything in a small number of steps. You immediately get a small diameter graph, which is also good. So I'm kind of leaving out details. Why does dropping the diameter by factor 2 make it easier? Turns out you can this is another measure of progress in the final algorithm, and everything just turns out to be okay. So that's all. Thank you.
We have time maybe for one quick question. Does any?
In this step where you repeated the half distance, you said at some point after log n iterations it's small enough that we can just assume it to be non-negative.
Right.
Can you maybe quickly explain why this small negative number is not?
Okay, right. So good question. So this is crucial using the fact that the weights are so all the initial weights are integer, which means that all initial distances are also integer. So which means that so you know that the initial distances are all integer, which means that if you round like 1 over poly n weight minus 1 over poly n weight to 0, then this only affects distances by like plus 1 over poly n. So you can imagine that pretending weights are 0, computing the distances, and then just using the fact that the initial distance must have been integer, just round to the closest integer. Does that make sense? So this is crucial using the fact that things are integer, otherwise there's no notion of scaling and things don't work.
Thanks again.
Okay.